Welcome to my talk. I'm Ange Albertini, currently working at Google, and I will talk about exploiting identical prefix hash collisions. This is not a crypto talk. It's about exploiting the file format tricks behind of them, which we use for, which we use for shattered and other kind of attacks. If you want to go to have the crypto perspective on the same attacks, then go for this talk, but to be honest, if you don't know what differential path, boomerang bits, and whatever compression function means, then you maybe not want to watch it. It's just, this is the real thing, and this is here about, my talk here is about file format stuff. Oh, and I'm not here to promote any brand or to sell any product. So in advance, nothing groundbreaking, no new vulnerability, nothing like this, just a look behind the scenes of the research file format wise. But on the other hand, there are very few talks on this topic. So I was like, I wanted to give a good idea of what the word, it's like an overall invitation to the domain, and there are very few talks on this. So I was involved in a few of these, in all this in the past. So in 2014, I worked on malicious SHA-1, which I will call Mal SHA-1, with Jean-Philippe Aumasson introduced me, and then I worked with Maria from TU Graz. Then I worked on the shattered attacks, so the actual first SHA-1 collision, and more recently on one issue of POC or GTFO, where we also played with hash collisions. And in all cases, we worked with modified SHA-1, SHA-1, and MD5. And the modified SHA-1 was not reduced round, it was just some constant were changed to different constants to produce collisions, but it was not that weakened. But it was in any way very different from the collision perspective, which we will see later. So 3 projects and 3 different hashes, but a bit the same state of mind and skill set. So type of collisions. So I will talk about identical prefix type collision, where the 2 files are starting with the same data. There is some divergence between the 2 files, and then there is some recovery, and then the end of the file has to be identical. So even though it's called collision, it's not like take 2 different things and make them collide. That's called chosen prefix, and at this point the hash is considered broken. So for example, SHA-1 was considered broken in theory in 2005. So identical prefix hash collision could be seen as a divergence and reparation, fixing, rather than total collision from 2 different points. And then there is second pre-image attack, where you find data to match another data's hash, and find data to match a hash, and these 2 don't exist in practice. So usually the first that comes in the history of a hash is identical prefix collision. It's the weakest, and it's usually overlooked because it's not really considered that broken. And chosen prefix is the one that at that point where you can craft a bad certificate and a good certificate, and at this point the hash is really considered broken in practice. But my goal is that, because identical prefix is usually overlooked, to make it having more impact, so, and maybe explore the possibilities that it's actually not that weak as an attack. And I will also mention hash collisions as IPC because of identical prefix collision in the rest of the talk. So for academics, that's how they present hash collisions, and they just show big blocks of hexadecimal, and there is no visual, there's no impact, so you can hardly convince Linus Torvald to move away from a hash with this kind of text. My role in this is, I don't play any role on the big computation part, especially on Shattered, the SHA-1 attack, where there was only a huge computation and effort. I just play a role at this part, determine the file structure. Then there is this big part that is unknown, that I don't play a role in. And then there are collisions blocks which are not determined because they are determined by the computation. And then the good thing is that we have at the end to have 2 valid files, no matter what happened here. So it's like planning and then hoping to land recovery, and there is a single try. So the impact of of my work was indeed to get something that is better than random looking blocks. Will it convince anyone to deprecate something? And just to give you an idea, Shattered took 6,000 years CPU and 110 GPU years of computation. No matter how many GPUs it is, it's a lot of computing power. And at the end, we would like something that is quite visual. So if it's reusable and you can make an infinite amount of difference from the same computation, it's better than just 2 random looking blocks. And these are Mal SHA-1 examples just for the. And so there are actually not so many papers on this, the research, on this kind of research. I will cover mostly this first one in 2005, the first one with some kind of better attacks, and then the 3 ones I participated. So in the Malcha one, it's Jean-Philippe Masson, and in Shattered it's Elie Burstein, who introduced me to a cryptographer, which I worked. So in this case, for the Malcha one, I worked with Maria, and in case of Shattered, I worked with Mark Stevens. And then we had fun with MD5 for the issue 14 of Poker GTFO. And Melisha Elliott was the one in starting the idea that we could do something for that, yeah, as a challenge. So the important point is that the constraint of hashes and format have nothing in common. So in case of a file format, you need specific bytes at specific values. And in the case of hash collision, so this is a collision code, collision generation code, it's bits and shifts and whatever, and this is very incompatible. So in practice, we'll just consider, because the collisions block are very complex, we'll just consider them random. But from one side to the other, what we know is the difference between the two blocks. So you consider them totally random, and they only differ by a mask. In the case of SHA-1, it's a XOR mask. In the case of MD5, there's XOR and also addition modulo 32, 2 power of 32. But the mask is more or less known in advance. So that's what you have to rely on, even though it's made of randomness. In some cases that we'll cover, the collision blocks may contain arbitrary values. And if the collision is very fast to compute, then you can actually compute a lot until you have a given value, if that's what you want. So basically, you craft your files with random blocks, and you hope that it will work, and then you apply the mask. And again, in the case of identical prefix collision, the two files start with the same content. Then there are two blocks made of random stuff. They are different on each other side. The difference is specified by this mask. This is different content, but that at the end of these blocks, the hash is back to the same again. So if you add whatever content here, the same identical content, the hash is conserved. But after this the computation depends on the prefix. So you define the prefix, then there is a computation that generates this block of randomness, and then you can add whatever you want. But you hope that you have valid files that are compatible everywhere, and that you can reuse more than once if possible. So for example, this is the case of the Shattered example, so the first SHA-1 collision. And you see that these two blocks are really made of a lot of randomness, and the differences are specified by these XOR masks. So you know, if you just have one file, you can immediately generate the other file. And indeed, when the SHA-1 collision was computed, I was just given one file. We computed it, here's one file. Generate the other yourself, because at this point it's trivial. The XOR mask is constant. So not all attacks use the same, even though Shattered took a lot of computing power, not all attacks are easy or hard to compute. So in the case of Shattered, what is very interesting is that the first byte that contains some random is different. So we basically will exploit this to, like I said, with the ski jump, to jump over and to make the rest of the randomness ignore it. Even though this was very long in terms of computation, while a collision of MD5, a fast collision of MD5 takes 1 second, but the randomness is in the middle. So basically, you cannot have any content that you can plan in advance here. So basically what you can do is you just brute force until you have some bytes you can use. But here you only have one single byte that you don't even know the value, but you know there will be, the only difference on the file will be there. And in the case of Shatter, you know it's already at the start, and this is what we exploited. So depending on the attack, it might be easy or not, and it's not relevant to how complex the computation is. And again, there are several attacks, even from the same hash. It's like really one attack gives you a special mask, a special differential mask, and one, even if it's the same hash. So these are two collisions of hash clash, and this is a very recent this is the kind of collision where you can have actually some arbitrary text in the collision blocks, which I didn't know was possible, and Mark Stevens pushed it to GitHub on this Monday. Just for you, that it was new for me, and even publicly it was obvious for a cryptographer, but it was not so easily obtainable. So this is a link directly to the right script, and so this attacks takes a bit more time, because here an MD5, a fast collision takes 1 second. This one takes 2 minutes, but it's faster than brute forcing just the bytes here, you know. And you can have some arbitrary content within some rules inside the collision block. And again, this is only public. This is only easily generatable since Monday. So with these collision blocks and all this restriction on structure, there are a few strategies that you can use. So the common one is that you just use the collision block as some data that will be just used by some code that comes later. So basically you just comment out the collision block by a mean or another, like starting with a hash or a comment, and then you add some code that will reuse this as pure data. Or maybe it's external executable, like in the Kaminsky research, that will use these blocks as decryption key. So one block will be the right decryption key, and another block, another version of the block will be the wrong decryption key, even though they have the same hash. So in this case, you just use the collision blocks as some passive data. And there is some code that will rely on this data in a comparison or in a blind decryption way. Now, another way that we implemented is just to either via the prefix that is before, or you just brute force to set some opcodes. So the advantage is that x86 jump is EB and then something. So basically, you need only 1 byte to be controlled, that it will be jump over to a specific address. And if you have a difference in the parameter of the jump, then you can just have to put 2 payloads at the right place. This is easy, but as far as I know, there's no real life consequence. Now, much more interesting and probably harder is a format strategy, where you will set up a header via the prefix or inside the collision block like we did for Mal-SHA-1, and then you will alter a value so that you reach 2 different data depending on the which of the files you're parsing. And then if you open with the same software, then it will end up with 2 different data. And it's even better, of course, when there are arbitrary amount of data. Exactly. And then each file contains 2 data sets, like 2 pictures, but in one case, the parser will be redirected to one file, to one data, and in the other file, it will be redirected to the other. Now, another trick that we also use is when you just use a file format top-down, like RAR or 7-zip, and you just concatenate them, and you just make the collision block start with the magic. Then if there is a difference there, then in one case it will disable the magic of the first file, and therefore it will see the second file. Simple trick, but worth mentioning because it works in the end. And in this case, you need to have some control or brute forcing on the final byte of the collision blocks. So the goal of all this is to find a way to get 2 meaningful files despite the randomness. So the strategy is that you write your prefix, then you put some totally random stuff, then you apply the block, the mask to get the other file, and you just hope that they both work reliably, they just show differences, and they don't fail any parsers. And of course, the more compatibility, the better. So then which formats? Well, for more impact, you prefer to have something universally used, preferably multi-platform, so there are not so many file formats. And of course, by end users, not an obscure, totally useless file format if possible. An option, preferably something with crypto, but certificates and crypto format are usually pretty restrictive, so it's not easy, or as far as I know, not possible yet with identical prefix collision. And again, then you want really as few parsers as possible, because if you have one file format you have to test on all, I don't know, JSON parsers, then it's nightmare. And if you have just a single parser, it makes your whole Q&A much easier. And of course, you might prefer something very visual so that the public understands rather than, oh, this is the Autodex 3D file format, something like this, you know. Now you can pawn your favorite 3D artist. Yeah. And the challenge are, of course, validity, so the specs, and again the specs, but also the compatibility with the actual file format, so exploring all the corner cases. You want them not only to look, but also to load normally, and of course, you want to make sure that they will be reusable with set the limits of which files will work and which file will not, so you explore all the code path, and all the header values. So you have to say, could it be a 0, could it be an FF, could it be whatever, just to make sure. And also, I really looked at the source to see, I am sure that in all cases the parser will be okay. So it's exploitation, but the other way around. You don't want to break the execution. You want to make sure that in all cases with unknown data, the execution will go fine. So it's kind of reverse exploitation. You abuse the specs and the file format to make sure that it will work in all cases. You want the user to think it's just a normal file. So the paper in 2005 was the first one with if-then-else exploits. So they explored PostScript, PDF, TIFF, and Word 97. So this is the kind of macro that checks the content of the value of the block and then behaves differently depending on the values. So all of these, the examples in this paper are if-then-else. So again, not header or not file format tricks. But still, there's already PDF, so why not using that one? That was the start of the research for, in our case, for Shattered. And so there's no widespread scripting language in PDF. There is only JavaScript and form calc, but they only exist in Adobe Reader. So basically, there are 6 families of PDF readers. So basically, if you want full compatibility, you cannot use them. Then there is only one obscure way to put some actual computation testing. It's when you can calculate a color space with a PostScript mathematical function. So basically, you set a color space, and the lookup buffer will point to the collision block, and then you say you say to print something with a graphical state, and this graphical state points to a function that here contains some multiplication, some mathematical operation in PostScript to say give me black or give me white, and then you have two image that will display something. The problem is, again, compatibility is not good. It works perfectly in Adobe Reader, but in other readers it just doesn't work. And on top of that, you cannot overlap. If you overlap some text, so you can change some stuff, but you cannot overlap a value with another, because in this case you have 2 texts overlapping. So it's quite restrictive. So it works, but only one reader and a lot of limitations. So for Malsha1, actually it was very restrictive. There was no prefix. So it's like directly start with randomness, and you can brute force because it didn't take so long to compute, but we couldn't put whatever value we wanted in the start. So first of all, we did a shell script if then else. So you have the collision block, and then you have a comparison, and just to say good or bad. We also did a concatenation, so rar and 7-zip, master boot record, and a JPEG that we'll show later, and also all are in the same file. So the problem in Malsha1 is that we cannot control 4 bytes in a row, so you cannot put a magic like most magic number, like I don't know, Coffee Babe or whatever, you know, doc file. So Windows executable looks like a good candidate, because at the start of the Windows executable you only have a magic of 2, and then the only meaningful value is this. The problem is that if you will have totally random values, I checked that I created a Windows executable of 150 megabytes, and that was the maximum value that would run. So if you think that this byte could be just any value, it doesn't work. So now, because I will talk a lot about JPEG, just a primer on JPEG from the file structure. So it starts with a very short magic, FFD8, so only 2 bytes. And then there is a structures made, they are called segments, and each of them start with FF something, and FF not 0. Because FF0 is special. So it's always FF and not something 0. And actually it's a recovery mechanism. If you install some complete garbage, then the parser will maybe corrupt the image, but it will just look for the next FF and not 0 to say, now what structure do I have? So it's a very tolerant mechanism. And also the length are on 2 bytes, and they are big endian. So they are very easy. If you put a 0,1 something, it will never too small, so you cannot learn back on the collision block, and you will not, like I will show, end up with a 4 gigabyte file, because you know that there's only 1 byte that will give you a range of difference of 255 on maximum. So the strategy was to declare a command and to have the end of the length, so again 2 bytes and big endian, starting a command that will be variable length. And in this case, you will either, there is another command declaration, and the command declaration will skip the first image, which will land to the second image, or in the other case, this length is actually longer, and in this case, you put another image data right at the first place. And again, with 01x6, you know you will not jump back in the blocks, because collision blocks are 64 or 128 bytes, depends, but never very big. And again, they will not be huge either. So in practice, that gives you that, FFD8, and then, okay, the same thing with actual structures. And what we did is that, again, this is the start of the file. So there is a lot of garbage. So what we enforce is like an FF and a D8 to put a magic signature. Then these chunks, FF E5 and E6, are not very standard, but it's fine. because in the end, they are ignored, and the parser still looks for a length. And in this case, you can again, we don't control where everything like where the difference will be. So basically, this will create two common blocks, the two ignore blocks. They are not officially the comment ones, but it works because the parser still ignores them, and then it will jump further. So even though there are very little control of the whole overall data, this is enough to say, this is a JPEG, and jump further at different landing points. We can even do them all together in the same file for more usability. Just the thing, we cannot combine JPEG and masterboard record because FFD8 is an invalid x86 opcode. So now, that was modified SHA-1 in 2014, and now the start of the idea to try and do the same with the actual SHA-1. And the attack behind the shattered attack, the theory was already published in 2013 by Mark Stevens. And basically, the idea was, you need an attack, you need the computing power and to put it in practice, and you also need a plan on the file structure because you have only one try, right? So again, I only worked on the researching the file trick, so that was in 2015. And then once the attack was computed and there was actually an actual collision, craft the files and make sure they work. So even though it was huge in computing power, the attack was actually quite more flexible than the modified SHA-1. The computation is very complex, and it was never tried before. So we have one single try, and you cannot say, hey, can you change something now? So we didn't have this freedom at all. And again, one single try. Then, unlike mal SHA-1, there was a prefix. So we could put a lot of stuff. We have some control. The blocks, there was no place for brute forcing, so the blocks were totally random. The mask, unlike mal SHA-1, was always constant, so at least it was more predictable. And the block starts with the difference we can use as a trampoline to jump further. So first, I knew that the mal SHA-1 trick would work, but we still wanted a new trick. And then again, PDF. There was a PDF trick I mentioned earlier, but one reader out of 6. So I really looked for a different kind of aspects in the PDF, but it never works reliably. And one funny thing is that when you do this research, the SHA-1 collision doesn't exist yet. So you have very little traction if you're with colleagues. It's like, I'm doing research on file formats for a potential attack that it doesn't exist yet. And people like, what did you smoke again? Something like this. So it was actually like, yeah, really you don't get people interested in it. Once it's computed, it's too late because then it should work. I mean, it's too late for my file format planning. So you plan something, you wait, and then it comes, and then it's too late to change any bit anywhere. So if you're not familiar with PDF and with my vision of PDF, I will be short. So this is a standard PDF. And here, these are PDFs have a lot of weird stuff if you look at them in details. And by all means, they should be invalid. But actually they work just fine. So basically, every PDF reader, and I know that pretty well, have its own quirk. So compatibility with PDF, and when you want to manipulate file formats, is a nightmare. So I created extreme PDFs for each of these readers, and they all work fine, and they all break on all the other readers on purpose, because I went to extreme ways to make them as crazy as possible, but still opening fine on their respective reader, and that's the landscape of the PDF, right? If you want total compatibility, you have to deal with that. So it was just a parenthesis to give you an idea of the PDF landscape is really not easy. So that's a problem. Does it work? But does it even display or behave normally? And you can get one trick on a PDF reader is easy, but getting a trick on all of them is very hard. For example, preview is more strict with JPEG structure, but it creates here you have a JPEG with the two JPEG displayed transparently on top of each other, and there's no transparency in JPEG anyway. So that was a first funny one. Or okay, if you put an unusual JPEG in a PDF, it can reboot a Kindle, for example, or take very long, or even if you have a very completely crazy JPEG in a PDF, then it displays glitches only in Adobe, because why not? Or here, the ratio in Preview, Safari are different in Safari, because PDF. So again, PDF is tricky. PDF trick with total compatibility, and we would really like to have complete different documents. It's not just a glitch that, oh, look, this pixel is green or this pixel is red. Yeah, it's not very, we wanted something better. So eventually, convincing that JPEG in PDF would work because the PDF embeds entire JPEG files, and the parameters of the JPEG can be referenced further. So if we change the JPEG, then we can still, the dimensions and the color space, if they are grayscale or anything, can be changed after the computation. And again, unlike PDF, they all use the same JPEG standard. So basically, if you analyze libJPEG, then you have reliability within the PDF world. And again, the proof of concept will not be 4 GB. We knew that already with MALSHA1, and they will work fairly reliably, and it will be reusable. So like infinite pair of colliding files. So of course, then I already did some research on the JPEG part. So I wanted to see, because we wanted not to just have 2 pictures, but because it's PDF, we wanted to have something that looks like fake documents, and you need a higher resolution. And we saw that there are some limitations that I wanted to overcome, and especially the first image has to be jumped over, and so the jump can only be 64K. So that is a lot of limitation. So for example, this is the example I used for MALSHA1. It's already quite low in quality, and it's already near the limit of the length of a comment. So at this stage, image size is limited to 64 kilobyte. Good for a photo, but not for a documentation. Now the trick is to actually, in the specs, there should be only 1 comment per JPEG. In practice, if you look at libJPEG, there can be any comment will be sparse, so you can put as many as you want. So instead, you put, for each segment of the first image, you put 2 comments, one small, and that embeds a trampoline that jumps over it. So it's full of trampoline between all the segments. So in one case, it really jumps over all the segments. So in this case, the segments, each of the segments is limited to 64 kilobytes. So already you can use a bigger picture. Now, the problem is that, of course, it would be too easy if it would be that predictable. The one that contains all the data that is compressed and coded with mathematical algorithms and so on, this part, this segment, the scan segment, the length is only the length of the header, and the rest of the data doesn't follow any rule of length. Thank you. So basically, it will grow linearly with the file. So, and it will not limit itself to 64 kilobytes. So then, of course, that was too easy. And in the case of the official example, of the official proof of concept, it's 228 kilobytes, and the image I was given, you have a single scan of 227. So that will not work. It's already, you would have to have something that looks that is much smaller or uglier. So again, a primer on PDF, on a JPEG. In JPEG, you have components. So basically, the components is not in RGB, but in brightness, so basically grayscale, and how much there is of blue, so the big zone of blue, and how much there is of red. So you can see the redness, the blueness, and the luma. So first, an image is decomposed in components. Then each scans, you know, when you have this blurry image that loads, you can have each scan containing some value, some definition, and each of the scan improves the quality of the image. So basically, you split the data in this case, so you can add either the colors, or you can even add some definition. So basically, with the progressive image, you have the same file, but smaller scan. So already we overlook this limitation in a small way. I mean, so basically, for this proof of concept, just saving it as progressive was good enough to reduce all the scans below 64 kilobytes. But let's explore further, because why not? So welcome to the JPEG School of Wizardry, because if you look at the JPEG official tool, there is a switches for modifying, switches for advanced user, and switch for wizards. And there is even a wizard doc in the official documentation. And this is what we're gonna do. So basically, JPEG-Tron, with JPEG-Tron, you can, if you are wanting to do wizardry, you can really specify by hand each of the scan, and then you can really customize to make it you can really say one scan doesn't contain the whole information, 64 bytes, but maybe 1 bit. And in this case, you can split. Really, you can have a bigger picture, and each of these scan will be smaller than 64 kilobytes. The problem is that JPEG-Tron is a bit inconsistent, and the actual documentation's example is broken. But you know, wizardry, you have to learn it the hard way. In practice, this image, so it's high resolution, it's quality 100%, and it's 860 kilobytes. And here are all the definitions that that I use for JPEG-Tron. So here the 0 is the grayness. So there are not so many colors. If you look at, there's not so much red and so much blue. So basically, there's more grayscale information and blue and red, and this splits the whole 0 to 63 spectrum to, in this case, several scans, you see? So basically, with this, you can actually have this image, even if it's quite big and high resolution, you can have it keep all its scans under 64 kilobytes. The thing is, you can even do that more, but then I made a completely crazy JPEG, and it was still standard in resolution. It was taking 7 minutes to load on Ubuntu, just for your idea. While it was pretty standard from the resolution and everything. So now another trick is that JPEG has a theoretical limit, a hard-coded limit of 100 scan, but just on writing. And if you just on reading, it doesn't care. So you can put, I think I made one with 2000 scan, and that was breaking Adobe Reader. But at least we could release a multi-page doc, but it's giving mobiles a hard time. So there was not really needed, but at least now you know it's documented in case. So basically, Shattered is a JPEG in a PDF. So far I was talking about JPEG, so we still want a PDF file. So the PDF prefix declares the header, declares the image, then reference all the image parameter later in the file so that they can be updated once the computation is done. Then you put the two image content, you split the top image with all this scans trickery. And one thing is because they point to the same parameters, they have to have the same dimension, so which we didn't need in SHA-1. And how do you say? And then you put the data, you put the values, and you finalize the PDF file. So basically, this is how it looks like. And this reference the properties, and the properties are behind. And then you can put the PDF content, and you can even put several pages. We'll see that later. And this is just a single image that contains all the page, and you can make them point only show a partial part of the image. So basically, it looks like you're browsing a normal document. We can actually do better. We'll see later. So now, this was just theory in 2015. I said, okay, I'm done. Now, 8 brain year, 100 GPU year, and 6,000 CPU year later, woohoo, we have a collision. Here is the file. And so here comes the randomness. 2 years later, the great wave of Stevens 13. And this happens. Hi, Ange, I did what you say. The file did not collide. And I can tell you, I totally lost my shit. I was not breathing anymore. But what happened? And there was a lot of, first, the readers have been updated. There was some corner case I still didn't explore. I lost a few years of my life that day, but anyway, after we celebrated and so on. But lesson learned, keeping notes, especially, I didn't know there would be 2 years of, almost 1.5 years of separation between the two. So keep notes, and proof of concept helps, but also a diary, and sometimes even a log of command lines, because when you're under pressure, that's what you compute that for is on you, then it really helps. Every little things help. And again, some bugs have been fixed in the meantime, so the landscape has evolved a bit. And that was a lot of pressure. But at the end, Shattered is real, and there was no zero bug reported, so the PDF were really compatible with everything. And we got the best Crypto 17 paper award, Pony of the Crypto Attack, and nominated for Peters Award, so academic, InfoSec, and antivirus community. If you want details, this is what the actual proof of concept look like. And I will just add some details. There is a hidden death, there is a very, SHA-1 is dead inside, but there is also this buffer that doesn't look like it has any point. And it was for production purposes. Basically it was to randomize every computation so that we would, the computation could say it would not work on the same file. So that was a kind of anti-collision mechanism for randomization of the process. So you could explain the rest, but that one was for production purposes of the computation. So the impact of SHA-1 is not collision resistant. The CV was updated, and it broke as subversion in practice. But subversion was using SHA-1 for deduplication. Do I know this file already? Oh, same SHA-1, okay. Hey, wait. Is it the same file? And it was checking MD5 for integrity, and then it was breaking. It broke instantly subversion. There was also another practice with BitTorrent, because BitTorrent used SHA-1 to do the checksum out of chunks. So internet does its thing. Within 5 hours, there was a generator that was available. Someone did the HTML version of that, and a CTF championship did there was a flag, and a big Bitcoin bounty claimed for that. So internet as usual. There was some very enthusiastic feedback, but we can do more. It's not just about full page picture. It's about it's actually a totally standard PDF with a weird JPEG inside. Any PDF element can be part of the JPEG. And well, so I'm running out of time, so we'll skip on the demos. I will go faster. So basically, it could be a multi-page document, as we saw, or a totally standard documentation with only a few elements replaced. And here is the official Shutter document. And it's, it's totally the official paper. But what I did is just I replaced 2 elements of the text. So, oh, I lost. Someone played a trick on me. Yeah, okay, it's back. So basically, I replaced my name here, the reference to my name, with another one. So here you can see that my name was replaced. And the only picture that is in the document was also replaced with another one. So basically, it's a totally normal document, but here there is a use of the picture. And I'm just using clipping to only show this part. And then again, I'm reusing this picture again to change another part of the document. So 99% of the document is totally standard. And it's just a few elements have been pointed to that bipolar JPEG, that colliding JPEG. So what's JPEG? JPEG is not strictly an image format. It's a lossy data storage, if you think about it, specialized for photo. And PDF takes it a bit too literally. So 3 out of 6 readers accept JPEG store data for anything else, such as page content. So this is the code in the page content to generate it. The browsers don't do that, but all the other readers do, the standard reader. So the problem is that JPEG is in theory lossless. So if you do 100% and grayscale, you don't have component mixing anymore. And because JPEG is using blocks of 8 by 8, if you duplicate the data 8 times, then JPEG becomes lossless. So you can reuse it, and you can say encode this data as JPEG, use it as page content, use the SHA-1 prefix, and now you have SHA-1 collisions working with something else. So no time to go through the demo, but anyway, it's fully vector text, and it's actually SHA-1 colliding with a totally different vector drawing that I did. So again, another kind of JPEG SHA-1 colliding proof of concept using the exact same prefix. And the fun part is that in the end, it's a JPEG, grayscale JPEG, and of course the text can declare colors because in the JPEG. Now we have JPEG as image, and JPEG as data. Why not both? So you put the data you want to be lossless, you store it 8 times, you append the image, and then the page content can reference itself. The only thing is that there is no page content terminator, so it could fail rendering. But in the end, you use a normal image, and then you put some code here that you duplicate 8 times, and this will be lossless. And then this code is actually referencing the image itself. So basically, you can have 2 colliding files, and this is a JPEG that is colliding with this one, and the code is different, and it's referencing the image again. And these ones are also SHA-1 colliding. So again, still the same only computation, but you have different kind of proof of concept that could be tricky at very levels. And the thing is, it's trivial to detect because you have the SHA-1 is dead at the start of the file, but now it's not so obvious that it's just different of JPEG. It could be anywhere else. MD5, we also did some work on MD5. MD5 is already broken, so nothing to see, right? You could think that, but it's still, why create only a pair of colliding files when you create 69 collision and to have 2 to the power of 609 files different with the same hash. So what's a collision in the end? Usually you want a good and evil content, you want them to have the same hash, but the other way around, it's just the content has changed and the hash is the same. So basically a hash coin is a file that shows its own hash. So it's a mental trick because you think, usually people think the other way. It's like, how do you know the hash in advance? And here it's the other way around. We actually use some collision so that you can switch the display of the hash to adjust the rendered value to the actual file's hash. So a fake hash coin is just a script that computes, that was basically faking it and always often comes with obfuscation. If you use a format hash coin, then basically a collision is like either take this file or take the next one. So basically if you add X collisions, you can have X plus 1 version of the same element. And then you change the content so that the right element you wanted to display is rendered. Data hash coin is you actually have 2 alternate contents of the same thing. So basically you can use this as 1 bit of data. So then you can put some code that will parse it and display. It's more efficient, but it requires some code to be executed. So in practice, I really want to show those. So this is, oh, sorry, wrong. So this shows the actual hash of the file. And this one is even better, I think. So it's the hash is 8895. So this is a file that shows its own hash in a very nice way, I think. So we did, Greg did it for that for PostScript. That was the first hashcoin ever, and then SPQ did it for GIF, and Mako did it for PDF as image and PDF as text. So MD5 sum and PDF to text give the same result. That's pretty nice. And Rodcam did that with the GIF and also with TIFF. And that was an example. This TIFF is 4 GB because one pointer will be huge. So you know, sometimes it's good that it's also good to make practical proof of concept rather than 4 GB. But here it's not possible. And Poker GTFO is an issue that contains articles about hashcoin, but it's also a hashcoin itself. So it's LaTeX generated. It's showing its own hash on the front. It's also an SROM polyglot. So the same file is a PDF and an SROM, which is also showing its own hash. But this is a format hashcoin and this is a data hashcoin. So at this point we're at 609 collision. And the last one is because there is an alternate version of the cover in the file and you can swap them and still have the same hash. So that's why we put 609 collisions. So now you know a cryptographic hash is really broken when we were really playful with MD5, and you think security relied in the past on this. You know, in the end we computed almost 10,000 collisions for fun. So it's broken, officially broken now. So thanks Mark Stevens for the toys. Other formats, just quickly, certificates. It's difficult to exploit as far as I know. Prove me wrong, please. You'll be famous, I would say. PNG, the strength, the signature is very long. The chunk types is coming after the length, so you cannot really, you would have some brute forcing or something. The length are on 4 bytes and they are little endian, so they can be huge. And there are CRCs at the end of each chunk. It's easy to make chunks that will be ignored if you just start with an uppercase. And the CRC is usually ignored, but you could easily end up with a 4 gig with a huge colliding PNG. So that's why we didn't go that way. And again, it's not a hash and one trick forever. It's not a hash, but an attack for a hash that gives you constraints. And these constraints may be compatible or not with the file format. So the same attack can be used with various file formats, or a file format, as we saw, could be used for several attacks even in the future. Which I did. The Mal-SHA-1 was reused later on the actual SHA-1. So real examples. The trick of Mal-SHA-1 was then used on SHA-1, then when we use it for making a hashcoin on MD5. Or when I published the PDF, the actual shattered prefix, then it was reused for HTML, so another file format. So basically, if you do a simple format trick with the already collided computed hash, then this could be used for SHA-2, for example. This could help already. And if you find something with certificates, that might break a lot more even in the future. So from a perspective, all this is just a bag of tricks, and crypto doesn't care about proof of concept because it was broken in theory in 2005. But on the other hand, attacks rely on proof of concept, and these are the attacks who convince people to deprecate, and you don't get pwned by the papers, but by their POCs. So again, a new format trick could benefit the existing hashes or a future attack on a given hash. And again, Shattered generate an infinity of colliding documents, and it broke subversion in practice. I think that helped to convince people to deprecate SHA-1, because maybe there was already some existing attacks like this in the wild, who knows. So we still have a few tricks up our sleeves. Conclusion is hash collision exploitation is a very niche domain, but it's so weird. You have to talk with a cryptographer, and you have it's very unusual, but the rewards are also pretty funny. And again, researching a file format manipulation could benefit a future cryptographic attack. So, and maybe those are already used in the wild, right? Just for your information, when I was asked for Mal-SHA-1, I saw no solution. I gave up for a while, but then I was challenged for something that made me improve on JPEG, and even eventually with that knowledge I succeeded for Mal-SHA-1, and that knowledge was the starting point for Shattered. And so don't give up. I gave up, but I kept that fidget spinning in my head, like learning more, side quests in an RPG. That could help you. And also one thing, some people say, oh, what you do is really great and I don't have all this discipline and something. And I also thought, oh my God, I'm not so serious and everything. But just instead, when I tried that, it never worked for me. I couldn't do something that actually I hated deep inside. I just do what makes you giggle like a 3-year-old, because this is exactly what file formats and hash collisions do for you. And then if you keep it doing that repeatedly, having fun, eventually you get feedback and recognition, and by then you'll have no reason to stop, and you'll be disciplined because this is something you love, and this is something you acknowledge for. So if you think, oh, I don't have the discipline, first think, what gives me real fun inside? Like me and playing with hash collisions at 2 a.m., whatever, you know. Thanks for your attention. And any questions? In the meantime, so this totally standard file, but this is actually an image. Then in the end, the only picture, I replace it with the commit, the commit strip comics. Then, slow. Will you crash? Will you crash on me? Oh, it should work. Hey. Oh, yeah. So this file is vector. And this is also SHA-1 colliding with the other one. It's all vector, so there's no JPEG image here. I mean, there's a JPEG image that gives the data to render the content of the page. No question?
I have a question. Why is talking to cryptographers weird?
Because I still don't understand what boomerang bits and differential path and compression function and whatever it is. No, it's not weird, but it's really good because you really have to find a common ground for understanding, and it's a different world. So that's why you need to translate. Basically, I remember when Jean-Philippe, where is he, explained me some stuff, and I was like, can you translate that in human words? And then I think I get it, but I'm a proof of concept person. So then I do a script that does this, and then I say, okay, this is how it works. And this is when I would understand. I need a Python code to do that. So it's not particularly weird, but it's challenging for both sides. And it's very interesting. And I'm very proud that both Maria and Mark sometimes suggested stuff from the PDF specs, like, whoa, I made a cryptographer look at the PDF specs. Poor them. But on the other hand, it's sweet revenge. Just kidding. By the time the microphone reaches away, if you want to grab home a file format, please help yourself. And if you use one of my posters in your work, feel free to sign my own copy of my Bible to convince my wife I'm not doing that for nothing.
Well,
So kind of reverse autograph.
This is not a question about, the exploit itself. It's about the time between the theoretical break of the hash and let's say the fact that it was really considered to be exploitable in practice. So it was a 10 years period.
Yeah.
So you said, okay, the algorithm was broken in 2005.
In theory, and that's what academics say.
Yeah, exactly. So, but when it is really considered broken, it's just when the theoretical.
I don't know. It's a crypto question. 2005, but why? Okay, that's. I don't know. For me, it's broken when I have colliding files on my disk.
Yeah,
so,
right.
but
That was the question. Is
Yeah.
about when it is really broken, when you can prove that the randomness is not is less than what is the theoretical one, when you find that the computational time is practical and you can exploit it,
Yeah.
or when you really find a collision.
yeah, exactly. It's three different vision of the same thing, right? So when it's fast enough in theory, when someone has enough computing power. So for example, the 110 GPU year took 8 days in practice. But or if you want an attack, then it's when you have the files on your disk. So you're right. All three are valid from different points of view.
So we are already late, so we'll take one last question.
And on the other side, if you're designing a format, or I don't know, like if you're collaborating with the team at Google that is making the WebP format, what would be the good practice to protect against such attacks?
Yeah, I don't have a quick answer for that, but definitely this is something I should write. So definitely, I never thought in detail about this, like what would be the perfect rule, but definitely even something like PNG has CRCs, but most of the time they are ignored. No, also enforcing the specs, putting some specs. I mean, a lot of stuff. The JPEG I put were not valid because the specification says that it should start with the actual header, and me, I started with something different. But in practice, in libjpeg, the code of libjpeg doesn't care. So again, the specs are not even relevant here. I looked at the actual code, and then I tested on all devices, iOS, Android, and everything, just to make sure. So there's no quick answer for that, and second, is it even relevant in the future because it's never enforced. Funny state of mind is once we had computed the collision, I was like, how lucky we are that the SHA-1 gives the result of all the platforms for the same content. And it's right from a mathematical and crypto perspective, but from a file format, it's absolutely not right. So I remember thinking, wow, they're fucking lucky cryptographers. But they are doing things right because specs test vectors, and if your SHA-1 implementation deviates in one bit, then you're wrong. Ooh, feels like German, but in the end it works. Thanks a lot.